Hi, I'm Dr. NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. Good morning, everyone. Good morning, dear students. Today, we are going to continue with our chapter 3, which is Dft, which means discrete Fourier transform. As usual, we are going to have some portions, for example, of 30 minutes. And then from there, we will have a pause so that we can understand, and if there is any question or anything, yes, you will have heard what I said. So today is going to have such a rhythmic movement of how we are going to discuss so that you can get the point. Yeah, so we are going to continue from where we stopped last time. Last time we talked about the way, how Dft is done, starting from its definition. Also discussed the properties. We discussed the matrix format. And today's subtopic is going to be Dft algorithm. So Dft algorithm. And this algorithm is going to help us to interpret or to compute the matrix equation, as we said, because now we discussed a little bit about the Marxist format of Dft. Remember, if I can remind you what we discussed last time, we said Dft is used to convert the signals in a time domain to their corresponding frequency domain, but using this Fourier transform or Fourier series. So the Fourier transform is going to be the output of what we need. And therefore, remember we came up with a equation where we said, for example, here we said big X of k being summation from n is equal to 0 of n minus 1 small x of n, of course, having the other exponential format, so which is j to pi nk, small k, over big N. So based on this equation, we are going to have an n big n terms, the n terms or n point. The endpoint here is going to be divided according to the number of frequencies. Remember, we are trying to make it simpler. The number of frequencies are going to be divided into a simple form in n times. And remember, according to the property of multiplication, as we saw last time, whereby at any point, we will have n squared. In this case, remember when we introduced about the equivalences of power, signals, and so on and so forth. For instance, you remember we discussed also some of the properties here. We said that is multiplication property. This is multiplication property. Property. But also we have for at any endpoint, we can have also additional property, of which is going to help us to compute our Dft transform. So the addition property is going to have n, for example, into n minus 1. whereby you will have a series of differences of numbers. Then it's like having the first term multiplied to the other, and so on and so forth. So for large number of n, for example, if we have large number of n, the number of computation is going to be also large. So, and this one, remember, it is going to be a time consuming. It's going to take time for the processor to process it. Remember, in the next chapters, we will discuss about the digital signal processors on their own. But in this case, we can take it like this. If you have a big number of n times, or number of frequencies divided into a huge number of time, then it's going to consume a lot of time. So in this case, we are going to also to have calculations of multiples of Dft, but it is based on addition and multiplication property. Say, for example, if we have n number, like if we have a n is equal to 4. So for replacing this property, so you have n squared, which is going to be 16. And also, in this case, is going to be 4 into 4 minus 1, which is going to be 12. So depending to a number of n times, then you can either get the table in terms of multiplication, in terms of additions. So you can have as many numbers of frequencies divided into n times. So in case of the properties that we have seen, it is applied accordingly. For example, you remember when we said that big Wn power nk, for example, is equal to E power j. It's the same thing of nk of n in this case. So in this way, you can transform any way you wish, so that you can get its equivalent. Suppose if you are given the value in this case, you can either translate it in this, and this one also can be translated into the Euler theorem, which is bringing the cosine and sine. So this one can be translated. For example, remember, it's going to be the cos, the 2 pi nk, for example, over n plus j into, okay, it can be minus, okay, 2 pi nk over n. In this case, it's also, it can also be applied in this case. So it is easy, you can just easily determine this value. And also, remember, this one also is going to help us in computing our matrix format of Dft in case where you have, for example, you remember when we calculated the W, we said, for example, at any partition, suppose if you have n at 4, then you will have, for example, n W0, W1, W2, W3. So you can compute as many numbers as you have or you want. So in this case, it can be a matrix format of, for example, a big X of 0, X of 1, X of 2, and X of 3 in its form. Then which is going to be equal to or for example, if you have W, in this case, going to be W all of the time, and so on and so forth until it reaches, for example, then here it will be W0, W0, okay, W0. Then you begin with 1, W1, okay, W2, W3, and so on and so forth. So you will have such a kind. And this one also is going to be its equivalent in xn, small xn. So this is going to be the inputs that you have provided, whereby we were looking for the frequency. We are discussing about this the matrix format of our DFT algorithm. So continuing from there, we discussed all these things, and we said, suppose if you have the W, you can get the corresponding cosine, which is a Twiddle factor, where we said, for example, if you have big W, big N, and then you have NK. So the NK, for example, is going to be, as I said, it's going to be E into J 2 pi N K over big N. So, and this is what we said, it is called the Twiddle factor. The Twiddle factor. Twiddle factor. So this factor helps us to even to convert its the corresponding cosine and sines of trigonometric, Euler theorem, whereby you can even, being given this one, you can find this one. Being given this one also, you can also do, or remember when we perform IDFT, which is inverse discrete Fourier transform. So the other way around is also possible, and we can calculate at any particular point given any particular value. As I told you, you can have x of 0, x of 1, x of 2, etc., etc. Then we will have, for example, the x of big N minus 1, which is going to be equal to the matrix format of this case, for example, given for any value at a unit step. Suppose if we are calculating at a unit step signal, then the first value is going to be N 1, 1, so on until at one point. Then you can also have some values. For example, at any particular point, you can have 1 Wn, because the other side is going to be squared, and then until it reaches to Wn, big N into N minus 1. Yeah, so like that is going also to be, okay, at 1, okay, this is going to be 1, okay, like this. So until it reaches to W, remember we are putting the squared here. If it is 1, it doesn't make sense. Then until it reaches N minus 1. So I don't know whether you are seeing this one, but this one is N minus 1 in this case. And then 1, like this, 3 N until it reaches W 3 of N minus 1. Like so, it changes from this value until it is reaching to any value there. And this one also is going to give the corresponding small x of n. The small x of n, z, x of 1, x of, until it reaches x of n minus 1 in this case. So I don't know whether you are seeing it, but that's how we calculate according to any values. So this is the case of explaining the matrix format. So we are looking for a big X. Remember, this is big X, which stands for frequency divisions, and this is nothing but the general format. For example, if we want to calculate big X of n in this case, or of k in this case, it's the normal equation that we used last time, which is going to be summation from n is equal to 0 of n minus 1, and so that the small x of n into, now in this case we are using Wn. So we are having Wn, big N, Nk. So this is the general format here that we are going to use. So in calculating this matrix format. Yeah, so it's very important to note, you have seen the way how the exponential format is increasing until it reaches to where we have stopped. So it's going to be the increment of n times, depending to how many numbers of divisions that you are using in this case. So we can end up having, for example, I don't know whether you are going to see it, but it's going to be x of 0, x of 1, x of 2. For example, if it is n times, then it will stop from 3. If n is equal to 4, then it brings its corresponding W's. So as I told you from the beginning, it's going to be W0, 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 then W0. Then in this case, we begin with, this side is going to be 0 all the time. And you can see going to be 0 elsewhere. But here we are going to be, it's going to change. This column is going to change. It's going to change in this case. And the other one also is going to be, this is going to be the even. So it's going to be 2, 4, 4, then for example 6. And then the other one is going to be beginning from W3, multiples of 3 is going to be 6, and this is going to be 9 in this case. So you can see this column doesn't change, but it begins from the second column having the multiples of 1s or multiples of 2 and multiples of, so this is even, the other one is of 3 times. Remember, it cannot go, if n is equal to 4, then you will stop at W is equal to 3, for example, because you begin from W0 in this case. So this is the format of, and remember we are multiplying, we are just supplying the input with, this is, okay, small x of 0, small x of 1, small x of 2, and small x of 3. So we are supplying, this is the input, discrete input, to get our output, which is frequency. We can easily obtain that one. So this is a matrix form of n is equal to 4. But it can change according to how many numbers of frequency you want to divide, or you want to have. For example, it can be n is equal to 6, n is equal to 8, n times. Using some of the properties, like symmetric properties, where we said we have a circle of real numbers and imaginary numbers, the negative values and some other values. So you can obtain, you can use a cosine where we can apply this side, because remember we have, if you have this one, you can either draw the circle from the origin, then you have, for example, some values according to how many numbers you want to get. So suppose if you have n values, beginning from any value from, for example, at n is equal to 0, 1, 2, 3, and so on and so forth. You have these values, and you want to supply them according to these values. Then you will have to convert this one into their corresponding cosine and sines, and then supply. So suppose if you have cos 0, then it's going to be 1, then sine 0 be 0, for example. So it will depend. So the value will be like 1. So you begin calculating the value depending to how many value that you can get. So suppose if you want to supply, for example, if we say at if n matrix is n, we are using 4, and in this case we can begin from example w of n4 of 0, then it's going to be the cosine. So everything is going to be multiplied by 0. Remember, j 2 pi nk over n. Everything is going to be 0 in between because we are supplying from n is equal to 0. We are multiplying by n is equal to 0, and therefore anything that is multiplied by 0 remains 0, and this is going to be j2 pi nk of the big N in this case. So you can see this element of n is going to be multiplied, and you end up getting cos 0 in between minus j sine 0, and this one makes 0, and this one cos 0 becomes 1. So if you can supply 1, if you can recall very well, then you supply anything. So it will remain cos j2 pi at, for example, at any particular point of k, then it will remain as some values. For example, suppose if k also is given some value, then you end up getting negative j. Okay, j, negative j, because it's going to be, one side is going to be 0, then the other one is going to be negative, then another one is going to be at 2, and so on and so on. You get some of the values. For example, here you get j. I remember we calculated this one in details. We are just repeating them until you reach to some values where you get 0. So at any particular point, you will sum up, and for example, you will end up getting wn at any particular point of at any point here is going to be the summation of plus, for example, minus j, then plus j, then minus j, in this case plus minus j. So it will end up becoming 0. It will have some point like 0. So you remember we calculated and just got some of the values here. In this case, we said if we are calculating these values, you are looking for the first term, where we said, for example, we have at w is equal to 0, then you can get the first term. So, and so on and so forth. So if you get the first term, second term, then you can supply it into our formula. You remember, in this case, because we are having n, then we have big N at 0, big X at 1, big X at 2, and big X at 3 in this case, which is going to be our value there. For example, if it was any given point, for example, you remember at I repeat this one because it's going to be remember this case where we said 0, 0, 0 in this case, and then W1, W2, W3. Then remember this side is going to be the multiples of 2, multiples of 6. Then the other one is going to be multiples of 3, 6, and so in this case. And you multiply with small x of 0, small x of 1, small x of 2, then small x of 3 in this case. So in this case, you supply what you have obtained from this value, then you put some of the numbers. So at this point, we obtained 1, so it is going to be 1 throughout. So it's going to be 1 throughout. or let me draw it like this. It's going to be 1, 1, 1, 1 for the first calculation. Then the second calculation is going to remain, or remember, at this particular point it's going to be 1, 1 throughout. And then at w is equal to 1, we obtained negative j. At w is equal to 2, we also obtained negative 1. And then we obtained j, like that. So we have also negative 1, 1, negative 1. Then we have j, negative 1. Then we have also negative j at this point. So which is multiplied by, of course, the other values of ours, which is a small x, this one. X of 0, x of 1, x of 2, and x of 3. So this is our matrix format. So you can see it is just becoming very smart according to the values that we have obtained from there. Then we obtain the other one. So you can see it is throughout. What we have at this point is the other one, at the other point is that one, until you reach to the values that you want. So in this case, you can have number of multiples. For example, at x of 0, suppose if you supply at x of 0 at your point, for example, you will have, for example, x of, remember our previous calculation obtained, at x of 0 we obtained 4, and at x of 1 we obtained, the rest we obtained 0. Remember the last time when we discussed, after computing, we got 0 at this particular point. So we got 0 in this case. So this case, after having this, if you cross multiply using matrix format, you can obtain this one. So if you use this one, you remember you divide this one, you multiply the inside, then you cut. So it will depend to, so you will easily obtain this value, and which will be our x of 0 at this point. So you can have a big X of 0, big X of 1, big X of 2, and big X of 3. So these are the frequency equivalent. So in this format, the matrix format is going to have this format. So remember, after obtaining the other values, you are going to have the multiples, for example, of 1s. For example, remember, if we have 1 in this case, and 1 in this case, and 1 in this case, and 1, and we multiply it with our simple x of 0, x of 1, x of 2, and x of 3. It is how this is stipulated. For example, then you put the other values of 1, negative j, then negative 1, 1 j. Then you have, for example, 1, and then negative 1. Oh, okay. This is j. Okay, negative 1, 1. Then you have, yeah, so it's going to be, okay, 1, negative 1. Then at 1, j, negative 1. Then you have negative j at this point. So, no, this is 1, this is negative j. So in this case, so you can easily obtain the multiples. For example, the x of 0 in this case is going to be the multiple of 1. So the way how it is done is going to be, for example, 1 times 1, that is the first term, plus 1 times 1 plus 1 times 1 plus 1 times 1 in this case. So you multiply, for example, 1 times 1 plus the negative j times 1. We are just bringing these values. Then negative 1 plus negative 1 times 1. Then j times 1 in this case. Then 1 times 1, of course. Then plus negative 1 times 1. Is it j? Yeah, it's 1 throughout, plus 1 times 1, then plus negative 1 times 1. So we are multiplying these values, plus j times 1, negative 1, then plus j times 1, sorry, then plus negative 1 times 1, then plus negative j times 1. Remember, we're having x more of 0, x1, x of 2, the x of 3. So, and that's where you will find, for example, you will find after having this, the results going to be the x of 0, x of 1, and x of 2, x of 3, like this, which is going to be 4. For the rest is going to be 0. 4, 0, 0, 0. It's going to be in this case. So, okay, I have put a space, but you can see. So the result is going to be this value. So you can easily say that x of 0, that is in frequency format, x of 2, x of 3, this square is going to be this format, 4, 0, 0, 0 in this case. So this is our answer in this case. So that's how we do it. So we sum up, because you remember we are using the summation of those points, and we are trying to come up with some of the results. So you can see this is what we have obtained. So, and this is the first number or the first calculation of our matrix format. So the next time we are going also to deal with some other properties.